Hello again. This is Math 2-115 coming to you from the College DuPage, and this is the continuation of the lecture entitled Sequences, Strings, and Such. Sometimes we will benefit from dealing with a summation when it's given by a formula, and other times there will be benefit from changing from the summation notation to expanded form. Let's look at two examples of that. So here to compute, the summation is k equal 1 to 5 of k squared. So we write it in its expanded form and say it is 55. When the upper limit of a summation is a variable, we can use an ellipsis, that's the dot dot dot, to write the summation in expanded form. So down here we have this. You write the summation as I goes from 0 to n of minus 1 to the j. Actually that's an I, minus 1 to the I over I plus 1 in expanded form. And so we write it that way. So we start at 0 and it goes 1, 2, 3 plus, but then it is dot 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 all the way up to we end with it being n. And then we can actually do a calculation here to simplify this, so we will get these values, and you see this minus 1 is going to give an alternating character to these terms, and then we can simplify it and we can say this is what we have. And we could evaluate this for various values of n. This is changing from expanded form to a summation notation. So we have this, and we want to write this way. And you see what's really going on is we're going from 1 to n plus 1. So the general term is going to be I plus 1, and we're going to start from 0. So you see, writing this in summation notation, this would be what we have, but that ends up being the summation I equals 0 to n of I plus 1 over n plus I. And sometimes I want to ask you to evaluate a sum. And so what is the value of this when, and we're taking n, and remember the n is the number that's up here. So n is 0, n is 1, and n is 2. And when you evaluate a sum like this, you can avoid a mistake by imagining it in summation notation. So this is a summation I equals 0 to n to I. So you see the n's of what you're putting up there. So if you go from 0 to 0, that just gives you one term, and that's going to be 1 because 2 to the 0 is 1. If you let I be 1, you get 2 terms that you sum, and the answer is going to be 3. And if you let it be 2, you get 3 terms, and the answer is going to be 7 if you finish that. A more mathematically precise definition of summation is called a recursive definition, and this is what it looks like. If m is an integer, if I sum from m to m, a sub k, I just get a sub m. But if I sum from m to n, a sub k, that's the same thing as summing from m to n minus 1, a sub k plus a sub n for every integer n that is greater than m. Now, when solving problems, and we will do this yet in this set of lectures, it is often useful to rewrite a summation using recursive form. I call that stripping off a term. It is sometimes useful to do that either by grouping commands using a single summation sign or by separating off, that is stripping off the final term. And sometimes in other courses you'll strip off the initial terms. So here's an example of using a single summation sign and stripping off a final term. So here we're saying write this plus 2 to the n plus 1 is a single summation. Well, you see you go from 0 to n with 2 to the power k, but then you have n plus 1. So when we do that, this final term ends up, we just increase the upper limit to be n plus 1. But now we are also here rewriting this. The summation is I goes from 1 to n plus 1, 1 over I squared, but we're separating off the final term. So we're just saying, oh, we're stripping off the final term, and that's going to be 1 over n plus 1 squared, 1 over I squared. Is going to be that sum. That is often useful. There are some sums that are called telescoping sums. Some sums can be transformed so that successive cancellation of terms collapses the final result, sort of like a telescope. For instance, observe that for every integer k bigger than or equal to 1, 1 over k minus 1 over k minus 1 is actually equal to, if you get the common denominator and do the subtraction, 1 over k times k plus 1. So use this identity to find a simple expression for this. So here we're summing from k equal 1 to n of 1 over k times k plus 1. So what happens is when we start doing that, we can use this identity where this is equal to that, and so we'll write it this way, and then we can write it in an expanded form. And when we write it in expanded form, we see that the 1/2 and minus 1/2 cancel, the 1/3 and minus 1/3 cancel, and so on and so forth, dot, dot, dot. And at the end, this simplifies to this. I often ask problems about this kind of thing. There's also a recursive definition for the product notation, and here they are. So this is the product from m to m. That's just the one term a sub n. But if I do this, this is the same thing as taking the product from m to n minus 1 times a sub n for any integer n greater than m. So now the question here is, well, compute these products. So this one and this one. Now this is product is k equal 1 to 5 of, you just take k. So you're multiplying these numbers together, and you get 120. Here you are looking at k over k plus 1, so you let k equal 1, then k equal 2, and you're multiplying all these things together. And so what happened is, but notice we're going from 1 to 1 only, and so there's only one term, and that is going to be 1/2. Now, these summations do behave, and there are ways you can simplify summations. Here you're adding up a's, and then you're adding b's, but addition, 1 plus 2 is the same thing as 2 plus 1, so we can change the order. So this is the same thing as adding the a's and b's together and adding them up. We also have a distributive property, and the c can be pulled, the c is a constant, in and out of the summation. That's the generalized distributive law. And multiplication also is commutative. So you could multiply all the a's times all the b's, but that's the same thing as multiplying a, b together. Sometimes this theorem helps you simplify things, and these proofs are by math induction. So here's some calculations to do. We let a sub k equal k plus 1 and b sub k equal k minus 1 for every integer k. So you write each of these as a single summation or product. So a and b. Well, what we're going to do then is, first of all, we're going to substitute in what are a sub k and b sub k. So that's what we substituted in. And then we start looking at the summations, but here we take the 2 and we put it inside here. And then what we're going to do is, since we're adding these and the indices are the same, what I can do is I can put the summation on the outside. I'm really changing the order. And then I'm going to simplify this using algebra. So k and 2k is going to be 3k, and this one is going to be combined with this minus 2, and so it's going to be 3k minus 1. So that's what would be a simplification of this. We can do the same thing with this. We're multiplying and the same things with a sub k and b sub k. We're doing here, first we make the substitution, then we use that theorem, so we multiplying all the a sub k's and then all the b sub k's, the same thing as multiplying those together, and we get this as a simplified thing, because this is an algebra identity. We know k plus 1 times k minus 1 is k squared minus 1. And another thing is to remember is that this is really a dummy variable. It's like solving an equation for x, and I could write the same equation using a variable called z. So here k is the index, so you go from 1 to 3k squared. That's exactly the same as I equaling 1 to 3 of I squared. So that is that's a dummy variable, and that's a change of variable. And the appearance of a sum can be offered by more complicated changes of variables as well. So for example, here if you sum from j equal 2 to 4, but it is j minus 1 whole squared, this is what we get. But when we simplify it, we get this, and that's the same thing as this. So you see these two represent the same sum, and in fact this would represent the same number. So this would be, both of these would be 9 and 4 is 13 and 1 is 14. And a general procedure to transform, well, okay, so that's a change of variable, and those will often happen. Okay, so let's practice this, transforming a sum by a change of variable. So transform the following summation by making the change of variable. So the summation is this, the sum from k equals 0 to 6 of 1 over k plus 1, and the change of variable is j equal k plus 1. Now you have to be mindful of the term as well as the indices when you do that. So first we calculate the upper and lower limits. So when k equal 0, j is equal to 1. When k is equal to 6, j is equal to 7. So the sum is going to go from 1 to 7. Next, calculate the general term of the new summation. You will need to replace each occurrence of k by an expression in j. So since j equal k plus 1, then k is equal to j minus 1. So that means that 1 over k plus 1 is 1 over j. So putting all those steps together, this summation, which we started with, can be rewritten this way using that change. And those will be representing the same thing. When the upper limit appears in the form of the expression to be solved, so here you see we've got an n inside, but k goes from 1 to n plus 1. We here in this problem, so we're going to rewrite this summation so that the lower limit becomes 0 and the upper limit becomes n, but the index continues to be k. So first transform the summation, making the change of variable j equal k minus 1. So we go through the steps that we did before. When k equal 1, j is equal to 0. So the lower limit is 0, and the new upper limit, when k equal n plus 1, then j is equal to n. So you see we're going to go, we're changing the limits. And now n is constant with respect to the terms in the sum. You see it's just a constant. The summation is on k. So therefore, k over n plus k is the same as j plus 1 over n plus j plus 1. So this is our general term. And so therefore, starting with what we started with here, and we make the change of variable, we get this. Let's do the same thing with the second one. Transform the summation obtained in part A by changing all the j's to k's. So this is kind of working backwards, and working backwards you see you get back to working backwards you have this. So we're changing all the j's to k's, and so what we're going to do is we're going to do this, but we'll get then that j plus 1 is going to be k plus 1, and so we get this, and you see now that's a dummy variable. It didn't matter whether it's summing j or summing k. You want to think about this for a while. And you can do that while you're waiting for the next video to load.